Okay, so first let us start with an example. Here, if U1, U2, U3 are orthogonal curvilinear coordinates. Our orthogonal curvilinear coordinates show that the Jacobian of x, y, z with respect to U1, U2, U3 is, this Jacobian is written as J within bracket. In the numerator, we have x, y, z. In the denominator, we have U1, U2, U3. U1, U2, U3. And this is also written as though x, y, z divided by though U1, U2, U3. And this is given by the determinant del x by del U1, del y by del U1, del z by del U1. Next, del x by del U2, del y by del U2, del z by del U2. Next, del x by del U3, del y by del U3, del z by del U3. This is the determinant, and this is equal to the product of the scale factors h1, h2, h3. We have to show that if U1, U2, U3 are orthogonal curvilinear coordinates, and then the Jacobian of xyz with respect to U1, U2, U3, it is given by this expression. Jacobian of xyz divided by U1, U2, U3 is equal to this. We have to show that this is equal to this. So let us start the solution. Solution. The given determinant is equal to this del x by del U1 I hat plus del y by del U1 j hat plus del z by del U1 k hat dot del x by del U2 I hat plus del y by del U2 j hat plus del z by del U2 k hat cross vector की cross multiplication. This is the vector product cross del x by del U3 I hat plus del y by del U3 j hat plus del z by del U3 k hat. So the given determinant is equal to the product of these three vectors. This is scalar triple product. There you go. or in short, box product. And what is this? This is nothing but del R by del U1. So this is equal to, del R vector by del U1. This is equal to del R vector by del U1 dot. Next, this is equal to del R by del U2, del R vector by del U2 cross, and this is equal to del R by del U3, del R vector by del U3. And then we know that this del R by del U1. Del R by del U1, this is equal to H1 E1. This is equal to H2 E2. This is equal to H3 U3. Okay, so this is equal to H1 E1 head dot H2 E2 head cross, this is equal to H3 E3 head. Okay, so this is H1 E1, H2 E2, H3 E3. And then this is equal to H1, which is equal to H1, H2, H3 scale factor. You group the three scale factors together, and then what remains is E1 dot E2 cross E3. Then what is E1 dot E2 cross E3? This is equal to 1, because these are unit vectors which are perpendicular to each other. So the volume of the cube formed by these three unit vectors is 1. H1, H2, H3. This is equal to 1. So, so we have proved that the Jacobian, which is given by this determinant, is equal to H1, H2, and H3. Okay. And let me make one comment here. Which is if the Jacobian equals 0 identically, if the Jacobian equals 0 identically, then del R by del U1, comma, del R by del U2, comma, del R by del U3. These three, these three vectors are coplanar. Are coplanar vectors, and the curvilinear coordinate transformation breaks down. That is, there is a relation between x, y, z having the form capital F of x, y, z is equal to 0. So for our study, we shall therefore require the Jacobian to be different from 0. We shall therefore require the Jacobian to be different from 0. We shall therefore require the Jacobian to be different from 0. Okay. So what are coplanar vectors? Coplanar vectors are really kind of coplanar vectors are vectors which lie on a same plane. Same plane number the vectors we call them coplanar vectors. Aduna del r by del u1 if my del r by del u1, del r by del u2, del r by del u3, if they are coplanar means if they lie on the same plane, then the curvilinear coordinate transformation breaks down, and there is no and there is a relation between x, y, and z of this form, and we shall therefore require the Jacobian to be different from 0. Jacobian z equating collided season Jacobian z equina say for example we have already written that dv. Okay, let me take a new sheet of paper. We have already written that the volume element dv is equal to h1 h2 h3 du1 du2 du3. So the volume element is written as h1 h2 h3 du1 du2 du3. This can also be written as the volume element is equal to this dr by, sorry, this is del partial derivative del r by del u1 dot del r by del u2 cross del r by del u3 du1 du2 du3. And this is nothing. This expression is nothing but the Jacobian of the transformation from xyz to u1, u2, u3, which we have discussed just a few minutes back. Wow. This is nothing but this is the Jacobian of the transformation. So this is the magnitude of the Jacobian of the transformation. This is del x, y, z divided by del u1, u2, u3 multiplied by du1, du1, du2, du3. So this is nothing but the Jacobian of the transformation, Jacobian. So we can also write it as this is equal to z x, y, z divided by u1, u2, u3. Okay, I think you don't need this here. And magnitude of this multiplied by du1, du2, du3. So the volume element in any orthogonal curvilinear coordinate system can be written in this form. Okay. So the easiest one is this, and this is using the Jacobian of transformation from the xyz coordinate system to u1, u2, u3 coordinate system. Okay. So that's all about volume element. Okay. So let us look at one example of the volume element. Volume element ke koi example hum yeng se ba. So When we talk about cylindrical coordinates, for cylindrical coordinates, for cylindrical coordinates, for cylindrical coordinates, what are the scale factors? The scale factors are h1 equal to 1, h2 equal to rho, h3 equal to 1. So I repeat, the scale factors for the cylindrical coordinates are h1 equal to 1, h2 equal to rho, h3 equal to 1. So the volume element, so from this expression, we can write down the volume element. Therefore, volume element dV is equal to h1 is 1, h2 is rho, h3 is 1. So 1 times rho times 1. This is rho. Rho times du1, du1, du2, du3. So for the cylindrical coordinates, what are du1? du1 is rho, d rho. And what is u2? u2 is phi. So this is d phi. And what is u3? u3 is z. So this is dz. So this is the volume element for cylindrical coordinates. Okay. So similarly for spherical coordinates. So for cylindrical coordinates, we have rho, phi, and z for spherical coordinates. Spherical coordinates. For spherical coordinates, and what are the spherical coordinates? Spherical coordinates are r, theta, and phi. What are h1, h2, h3? The scale factors are h1 equal to 1, h2 equal to r, h3 equal to r sine theta. R sine theta. I repeat, h1 equal to 1, h2 equal to r, h3 equal to r sine theta. Therefore, the volume element dV is equal to h1 times h2 times h3. So this is r square sine theta. I repeat, this is r square sine theta dr d theta d phi. So the volume element is r square sine theta dr d theta and d phi. Okay, this is fine. So let us look at how to express gradient, divergence, and curl in orthogonal curvilinear coordinates. In orthogonal curvilinear coordinates, how do we express the gradients, gradient, divergence, and curl in orthogonal curvilinear coordinates? I hope you are familiar with gradient, divergence, and curl. Okay, if you are not, let me give a brief review of gradient, divergence, and curl. These are vector differentiations. So let me take a new sheet of paper here. Let me start with the vector differential operator, del. Let me start with the vector differential operator. The vector differential operator. Vector differential operator, and this is given by this we call del, and it is written as this nebula, an inverted triangle. This is read as either del or nebula, and this is defined by and this is defined by del or nebula. This 3-line stands for definition. In Cartesian coordinates, this is defined as del by del x. So since I have pronounced it as del, so let me pronounce it as do. So do by do x I hat plus do by do y j hat plus do by do z k hat. This is a differential operator, and this can also be written as I hat do by do x plus j hat do by do y plus k hat do y do z. This operator will operate on some scalar or some vector. This operator is also known as nebula. And this operator is useful in defining 3 quantities which arise in practical applications. And these 3 quantities are known as gradient, divergence, and curl. So let us start with the gradient. Okay, the gradient. Let us start with the gradient. Okay, let phi x, y, z be defined and differentiable. Be defined and differentiable at each point x, y, z in a certain region of space. Okay, I repeat, let phi x, y, z be defined and differentiable at its point x, y, z in a certain region in space. That is phi within bracket, that is phi defines a scalar field. Phi defines a differentiable scalar field. Differentiable scalar field. Scalar field means this phi is defined at each point in a certain region of space. Such quantities are called scalar fields, and since phi is differentiable, we call it differentiable scalar field. So phi is a function which is phi is a scalar function which is defined in a certain region of space. Okay. Then the gradient of phi. Then the gradient of phi, and it is written as this del phi or grad phi. Grad phi is defined by del phi is equal to del by del x I hat plus, we have known that this del operator is del by del x I hat plus del by del y j hat plus del by del z k hat. Okay, so so del phi equal to do by do x I hat do by do y j hat plus do by do z k hat. This will operate on the scalar field phi. Okay, now each term will operate on phi individually. So this can also be written as do phi by do x I hat plus do phi by do y j hat plus do phi by do z k hat. There we go. So this is the gradient. This is the gradient of the scalar field phi. And this gradient of phi, this defines a vector field. You see that this is the x component of the vector field. This is the y component of the vector field. This is the z component of the vector field. So the gradient of a scalar defines a vector field. Okay. Okay. And one more thing, the component of a that we write it down here. So here, grad phi defines a vector field. Vector field. Okay. Next up, the component. The component of del phi, that is the gradient of phi in the direction of a unit vector a hat is given by grad phi dot a hat. This is a vector, and I'm taking the dot product of this vector with a hat, and it's called the directional derivative. And it's called the directional derivative. The directional derivative of phi in the direction a hat. And what does this mean physically? Physically, this means this is the rate of change of phi. This is the rate of change of phi at the point xyz in the direction of a. I repeat, this is the rate of change of phi at the point xyz in the direction of a. That is the physical meaning of this directional derivative. Okay, that is gradient. Now let us move to divergence. Let me take a new sheet of paper. Okay, the divergence. The divergence. Okay, let v x, y, z. Let this be equal to v1 times I hat plus v2 times j hat plus v3 times k hat. We defined, let this be defined and differentiable. Defined and differentiable at each point. At each point x, y, z in a certain region. In a certain region of space. That is, V defines a differentiable vector field. V defines a vector field. Then the divergence of V written as divergence of V, or the V is defined by, this is defined by divergence of V is equal to dou y dou x I hat plus dou y j hat plus dou y dou z k hat dotted with v1 I hat plus v2 j hat plus v3 k hat. When we take the dot product, what do we get? We get del v1 by del x plus del v2 by del y plus del v3 by del z. This is like the dot product of two vectors. Here we are taking the dot product of the del operator with the vector v. So divergence of v is del v1 by del x, del v2 by del y, del v3 by del z. Okay, and we should remember that divergence of v is not equal to v dot nabla operator. These two are not equal. This is like a dot product, but here it is not commutative. These two are not equal. Okay.